Welcome to day two. We have a few more guests. Maybe we'll introduce them at the coffee break. Logistics. So today, some of us are going to the Bell Museum. So as a reminder, so we'll run the morning session. So the plan is that I will introduce ZTF and talk a bit about our filtering system called Boom. And then Theophile, who is online, is going to lead the demo. Antoine, who I'm sure is also working on his part last minute. He was here yesterday and he'll be here hopefully shortly. He will be introducing the mobile application that we have that is going to go with this. And so we'll be hopefully doing a full tech demo today and give you a chance to play around with filtering some ZTF data. And so we're starting a little backwards. So you notice we're going to talk about ZTF today. So what is ZTF? So first, it's an instrument. It's a 16 CCD camera. It's 600 megapixels. So almost a 50 square degree field of view. It has 3 different filters. And so yesterday, when Christina and Shar introduced Rubin, you spent some time playing around with the Rubin filters, U, G, R, I, Z. ZTF just has 3, G, R, and I. The Rubin CCDs are deep depleted, which means that they're more near infrared sensitive than the ZTF filters, for example. And so it's one of the things that makes Rubin special. The CCDs themselves span a wider set of band passes. And just like Rubin, the nominal exposure time is 30 seconds. Now, that is for the survey, but depending on if we're going to do some target opportunities, things like gravitational wave follow-up, sometimes we'll go deeper with ZTF. But 30 seconds for ZTF gets down to something like 20 and a half on a good night. For Rubin, for comparison, as you saw yesterday, is much closer to 24 and a half, 25. And so, very, very different sensitivities. But as I tried to argue yesterday, when I was introducing this, we do believe that working on ZTF, there's a lot of parallels with the way that we're going to be analyzing Rubin data. And so while today, when we introduce Boom, we'll be focusing on ZTF data. As promised, we'll show off a little DP1 data. You'll be able to see some of the early data from Rubin and get to play around with it a little bit. But broadly speaking, the techniques are very similar. And so ZTF is one of many wide field surveys. There's the dark energy camera on the Blanco, Sloan Digital Sky Survey, PTF was also on the Palomar 48-inch. It was the predecessor to ZTF. Pan-STARRS, which is on Haleakala in Hawaii, and then LSST or Rubin, which we talked about yesterday. And one of the points of the summer school is to introduce the idea that we are able to analyze multiple optical surveys simultaneously, and the techniques that we need to be able to do so. And so the building synergies between access to a variety of these surveys that are running. And so, as I mentioned, so ZTF's mounted on the 48-inch on Palomar. It's been running robotically since the early 2000s, which those who know, it still remains a bit rare. Now, many of these other surveys that we're talking about, it's becoming more and more common. Rubin will run completely robotically, but it is one of the transitions that's happened even in the last 10 years for either for surveys or for follow-up instruments. We'll be talking about SED machine in particular tomorrow when we get to spectroscopy. And given how long the 48 inch has been around, it's been running goes back in time, even back to using plates. And so there's initiatives at Caltech to try to do photometry over the last 50 years or so. And so it's used by a lot of people. This is a picture from the Stockholm meeting last year. This was the most recent ZTF team meeting. And just to brief background on the name, Fritz Zwicky is an astronomer who's well known for a variety of things: supernovae, neutron stars, dark matter, gravitational lenses, and so it's named for Fritz. And this is also the when we demo the SkyPortal part of Boom today, we put it on a different server, but this is why many of you who use the SkyPortal instance within ZTF, we call it Fritz, right? And so it's Fritz Zwicky. And so the transient part. So we've been talking about transients yesterday, so don't have to go too deep here. But the idea is that we are interested in things that are changing in the night sky. And transients cover all sorts of time domain phenomena, from solar system objects, comets or asteroids, to stellar explosions, collisions of black holes and neutron stars. So Char and Christina demoed yesterday the Rubin kilonova work, even exoplanets, although it's a science case that these surveys aren't exactly defined for. And so the idea is that these surveys, Rubin, ZTF, pan-stars, they're taking repeated observations of the night sky and we can use them to look for changes over time. So changes in either in stars or in transients, and use those to study them. And so what is so we talked about light curves yesterday. Broadly speaking, on the y-axis you have brightness, on the x-axis you have time. And so when we get to tomorrow, when Felipe will be introducing the machine learning classifier for photometry, we'll be getting to play around with how to do light curve classifications. And then Daniel on Thursday will be talking about our scope, which is our variable star classifier, and he'll be getting to play around with that some. So we'll be getting a lot of time with light curves over the next few days. And so in facility, and it's meant to represent that these days time domain astronomy is to some extent automated, right? And so one of the goals of the summer school is to demonstrate the data science techniques, in addition to this instrumentation that's been developed, to make discovery routine, right? And so this is Palomar. So the 48-inch is on the left-hand side, which has ZTF, the 60-inch, which has the SED machine, and then the 200-inch, the Hale telescope, which has both the spectrograph and photometry. And so it is kind of a one-stop shop to be able to discover transients or discover objects, as well as do classification. And so throughout this week, we'll be getting practice doing both. Today, we're going to be on the discovery side.
What's the marked one? Like just to the right of the P200. God, that's great. That's a big shit happening.
I don't actually know what's in that dome.
There.
Yeah. Okay. Right. So but there is a step between discovery and classification, and that is identification, right? And so as we talked about yesterday, right, you can get access to these alert streams, you can get access to this data. We will learn how classification works, but identification is this tricky piece, right? How do we go from data to identifying the interesting objects that you might care about? Right, so what does discovery look like? So the way these surveys work is you're taking, say last night, a new image, you discover some new smudge in some relatively nearby galaxy, and relative to a reference image, which is constructed using stacks of old images. And so the reference images that ZTF most commonly uses goes back to the time that the survey was starting in 2017 and 2018. And algorithms are used to then subtract these two, the new data from the old data, to create these subtractions. And this is how we discover new transients. And so we use the SOGI algorithm. We can talk about it more, but there's a variety of sort of open source software that lets you do this. This is actually both a computationally and kind of theoretically challenging problem. While the idea of doing subtraction kind of straightforward, right? Take the new one, subtract the old one. Things like matching point spread functions, astrometry, et cetera, actually makes this pretty hard. But folks have become quite good at this point. And so every time then something new is discovered, you get these what we call cutouts. So these order 50 by 50 pixel images around this new transient, in addition to information about the candidates. And so this is things like the magnitude or the brightness, the time, the position, some machine learning classification scores. Benny talked a little bit about this yesterday, and of course, we're going to get more practice with it today and tomorrow, in addition to all of the previous information. And so, since you're repeatedly imaging the night sky, you don't just get one data point, you'll get many data points. And it's these many data points that allow you to build light curves. And so this is what's released in both the ZTF alert packets. As I mentioned, we'll get some practice with sort of the DP1 data products. Now, the Rubin schema is still in flux. They're still taking feedback, and some folks have been participating in that, even in the summer school. But broadly speaking, this is kind of what you get, even if the sort of the names of things change a little bit. And so in these alerts, so you get that information for every 5 sigma fluctuation that's identified. This is processed at IPAC, which is at Caltech. And for ZTF, you get around 500,000 per night. For Rubin, as we mentioned yesterday, that number is much closer to 20 million. And so, while the techniques we're going to use for ZTF are, as I've been trying to argue, let's say appropriate, or for Rubin really is a different scale, right? This is, at least a factor of 20, if not closer to 100, depending on the night. And so even some of the work that's been done that works fine for ZTF, may not work for Rubin, right? This order of magnitude or two change, it's caused at least us to rethink how we're going to go about doing Rubin filtering, and that's why we're working on Boom, which we'll introduce today. But broadly speaking, these alerts, they go into brokers. There's 7 or 8 ones that are approved for processing Rubin data. So this is one point to make. In general, and this is true for both ZTF and Rubin, you don't get these alerts in real time just going to some website and downloading them. That's not how it works. You get access to the alerts through these brokers, partially for cost considerations, right? It's actually pretty expensive to just allow anyone to pull data off of a Kafka topic. And partially because these brokers are designed to, let's say, facilitate the data in a way that you can do your science, right? Because just handing someone, even order of 1 million alerts, it's actually pretty hard to figure out what to do with it. Yes, and so as I mentioned, going from these alert brokers, which we're going to play around with today, this is where the data goes to the community. Okay, so then the question is, with regards to these brokers, how do you find what you are looking for, right? In the, if I have 1 million alerts, I have 20 million alerts, it's too much data, right? And most of it's not interesting, at least to everyone. And so the idea is we need to identify techniques to down select that data stream to the objects that you care about in a way that is computationally plausible, and allows you to write the science papers that you're interested in. And so this is what we mean by this identification step. And so with ZTF, we cover something like 1/2 of the northern sky. It corresponds to about 2 terabytes of data, 500K alerts. And then now in addition to, the real objects, we're also identifying all sorts of artifacts and bogus detections. And, again, these machine learning techniques, which we'll talk about over the next day or so to deal with that. And so, to manage this, we need to be able to store large volumes of data. We need to figure out how to deal with the bogus alerts. We have to also filter out those objects for which we are not interested, and then visualize interesting objects, right? So this is, I would say, is the job of these brokering and marshalling systems, right? It's their job to help you, see the objects, figure out what you care about. And so when it comes to data storage, broadly speaking, this is the job of the surveys themselves. And so ZTF stores images at IPAC. There's a similar system for Rubin. And this is why it's typically just the alert packets and cross-match catalogs that these brokers deal with. And so in some sense, you can think of brokers they're just basically databases, right? And so the reason this is relevant is their data storage as well as data query, right? Because if we are dealing with order, 1 million, 10 million alerts per night, very quickly that means we're at, multiply that by 300 or so, per year. We really need modern query techniques to be able to manage these data scales. And so this is why all of these brokers are built on, modern database schemas. We won't go too deep here, but there's 2 types. There's let's say two reasonable choices. So that's kind of a dangerous word for database schemas for this kind of data processing. So one is a relational database or SQL based. The idea here is where you have various tables and they're cross-matched between each other by indexes. And so you can relate tables one to the other. There's the plus side is that you define the schema, right? And so if you know what your data looks like and you are pretty sure that the data is not going to evolve at least too much in time, because as your data evolves, you need to change the schema. In principle, these relational databases can be very, very fast, right? And so this is a common choice for at least some aspects of what we're talking about. Non-relational databases is the no SQL type solutions. They don't have schemas, and so these can be nice because for example, the alert packets that we're talking about, they do potentially evolve in time, and the format that they have do change between different surveys, and so it can be nice because if you can put your data, for example, in some kind of JSON format, you can dump it into a non-relational database and use those kind of techniques to do the queries. This is what we'll be using for Boom. We'll touch a little bit on relational databases when it comes to SkyPortal. Again, for a lot of this is in the weeds, and for those who are interested, we can talk about it more. One of the goals for Boom is to abstract a lot of the specific queries away, because this is, I would say, the database query aspect can often be one of the most limiting factors for astronomers to, be able to get at data. And so we're building front ends to try to, make kind of like drag and drop type, queries to be able to simplify uh, these instances. Okay, so when it comes to storage, it's not that bad, at least for ZTF. Broadly speaking, data transfers are fast, storage is cheap, databases are very performant these days. The alert packets themselves are much smaller than the raw data, right? Of course, the largest piece of this are the three cutouts around the transients, but this is a lot cheaper than saving the entire image into the database. So while this isn't an issue for ZTF,
I was just saying, does ZTF do it locally or is it managed through like AWS or something?
We run Kowalski locally at Caltech. So if we're talking about ZTF, it's less than 100 terabytes at this point on a local cluster at Caltech. But again, for Rubin, trying to save all alerts, depending on your system could be a challenge, right? So it's not a given that necessarily these brokers are going to save all the alerts, at least from the start of the survey to the end, right? And this could have disadvantages, right? There's benefits to being able to go far back in time. Igor, who's in the audience, one of the algorithms that him and Sarah, who's also in the audience, work on, historically has asked, have there been any transients historically at a given location? If so, reject them because they're probably not new. Something like this query may be challenging for Rubin, at least as the survey goes on. Okay, so so we also need to, of course, avoid bogus alerts. So there's a variety of machine learning models out there. As I mentioned, we'll be playing around with more of them tomorrow. ZTF's got its own, we call it BRI, which produces this what we call deep real bogus score. There's a ton of solutions for this out there, right? This is, I wouldn't say it's a solved problem, but it's a mostly solved problem. But the idea hopefully is straightforward enough. You take a set of classified bogus alerts, you take a set of classified real transients, and you create a classifier to try to remove the bogus. And so the score varies between, for us, in our alert packets, varies between 0 and 1. As the score gets closer to 0, it's more likely an artifact. As it gets closer to 1, it's more likely real. Okay, now for the filtering part. This is kind of the bread and butter of what brokers do. There's a couple of different approaches, and it actually changes how you think about this quite a bit, server side or client side, right? And so what I mean here is, where are you actually running this filter? Are you running the filter at the place that this broker is? In our case, are we running it at Caltech, or are you actually running it on your machine? And this has implications for sort of how people use it, right? Everyone wants something different, broadly speaking. Everyone has different science cases, and that makes one answer better than others. And unsurprisingly, though, there's still a lot of redundancy. For example, a lot of folks in this room are interested in extragalactic transients, right? A filter to remove galactic transients is a piece, for example, just either cutting off of the galactic plane, or maybe something like a star galaxy classifier. There are basic pieces of filters that a lot of extragalactic filters use. And so you would like ways to be able to not have to repeat this part of the filter over and over again for everyone who wants that. One of the shortcomings from the Kowalski, this kind of original ZTF version we were repeating this over and over again. That will not be the case for Boom, again, to try to make this all fast. And then multiple degrees of automation. There's a lot of machine learning used in a lot of pieces these days, and we touched on this yesterday, and we'll be touching on this, again throughout this workshop. We have examples where we have run ZTFs taking data, alerts are coming in. We have a machine learning classifier that it just says I'm interested in this particular transient, automatically triggers spectroscopy. That spectroscopy comes back. Another machine learning classifier identifies it as a type 1a supernova and then automatically posts it to the transient name server, all without humans in the loop, right? The amount of automation that's present these days is quite incredible, right? And so this goes all the way back to the filtering that you're doing. There's also different degrees of complexity, right? So you can imagine very, very simple filters like I just want any sort of transient that I believe is real, right? So that's as simple as choosing a deep real bogus score that's close to 1. Simple enough. You can have much, much more complex filters. Again, picking on Igor, the filter he runs, he actually tries to measure the rise rate and the decay rate of the transient and make selections based on that, right? So that means that not only are you demanding that your transient is real and it's extragalactic and it's got some hopefully high star galaxy classifier score, but now you're talking about actually measuring properties of the light curve and making decisions upon them. And so all these brokers have to be able to manage both sides, right? No matter how complex. And of course, some are very loose and some are very constraining. And while this may not seem like a big deal, now we come back to this issue of data rates, right? So if I just produce a really an alert stream from Rubin, for example, that's just all objects that have real, high, deep, real bogus scores or something, I will once again have a huge flood of data, right? And so we need to be able to manage sort of how we deliver that data to the community because indeed, you could just sort of be reproducing the alert stream if you're not careful. Yes, and so the point is, there's no, and we're going to hope to, part of the goal for, today and tomorrow is to demystify some of this. There's no secret ingredients here. It's just the stuff that you care about, right? And so it's you identifying the science cases and the most efficient way for you to down select these alert streams to get the science you care about. Okay, so this is the this bright transient survey bot, as we call it. This is a relatively simple example that we've had a fair bit of success with, right? We put some real bogus score. We constrain the age to be, the object can't be any older than 7 days. It needs to be brighter than 18 and a half. And we put some constraints on sort of previous activity. Okay, so how do I look at the objects that pass my filters? And so there's a variety of different ways that you will do this. Some brokers run web applications, right? So this isn't true for all of them, but some allow, have interfaces where you can click around and play around. About as common is where you're using the API of the broker, where you can query for objects that pass some alert stream, and then use your own code to plot the objects, right? So this is common, for example, something like Ample, fits in this schema. And then of course there are these multi-purpose astronomy platforms that the community is dubbed marshals, and there's a variety of these out here. I've mentioned SkyPortal, but there's also, Tom Toolkit, Easy Peasy, others that, others use to make this happen. So Alerce, which is, I got to say, a really excellent broker, has a really excellent interface. It's very easy to use. I'm a big fan. So you can, so Alerce is a good example here. And of course, as I mentioned, Jupyter notebooks, Python notebooks, whatever to do your thing. And then, we'll be playing around some with SkyPortal today, so you'll get to see that. And so the idea of these, whether you're using marshals or you're using, your own code to query some alert stream from some broker API, you're going to be doing scanning. And so the idea of scanning is not everything it's very, very hard, and dare I say, it's impossible to write a perfect broker, right? Where the filter that you have only produces objects that you care about, right? No matter what, no matter how good your machine learning classifier is, you're never, nothing's ever going to be perfect. And so it's very, very common still to do what's called scanning, which is look at the objects that come out of your filter. And so this is a view from within SkyPortal, but broadly speaking, what people do is they look at not only the cutouts that ZTF produced, but for example, cross-matched images from other historical surveys, Pan-STARRS, DS, whatever. And then also look at the light curve and any sort of other annotation data products, for example, machine learning scores, age, whatever, things that are on the right-hand side here, to try to decide, is this object real? Does it pass my criteria? Maybe I want to get a spectrum, whatever it is. That's what people do. And so for the objects that you've decided are of interest to you, they're good enough. At least in SkyPortal parlance, we say that we save them. And these are the objects that get saved to the database, and you can do things like trigger follow-up from. Okay, and then finally classification. And so the reporting discoveries within the community is critical. And there's a variety of ways that one can do that nowadays. So I already mentioned the transient name server, which is an IAU supported web application that, for example, simply like assigns names to astrophysical transients, which is a surprisingly challenging thing. I know, Eric and Corey in the back here are thinking about this for GRBs. But this is where this is done in the optical, at least currently. And so if you go to TNS, you can get information about a transient, whether it's from ZTF, Pan-STARRS, Rubin, et cetera. Broadly speaking, one of the difference between, for example, TNS and a broker, TNS, typically people will upload maybe a photometry point or two, maybe the first spectrum. Brokers and marshals is typically where you see the full data set. So it's not where you go to see everything, but at least, it's a place to, for the community to kind of put their stamp on it and say, I found something. And so broadly speaking, we want to know what an object is or what it isn't, right? This is the classification part. And so, we'll be talking more about spectra tomorrow. Okay. So just to highlight here, so as part of Apple Cider, so we've done some images, we'll do photometry, we'll do spectra, and at least within ZTF, we typically rely on the SED machine. At this point, we're at around, we've passed that 10,000 supernovae number. And so you can see how the night sky fills in here. And so one point to make, because spectroscopic resources are limited, you can't classify everything. Typically, these surveys, especially something like Rubin, right? You're gonna discover way more objects than you possibly have time to classify. And so the prioritization part is critical. Right. Again, we're coming back to the science cases you care about. What is the subset of events that one is possible to get spectra of, but two, interesting to get spectra of. And so, for example, working with an Apple Cider or whatever other framework to focus on anomalies or rare transients, this is the kind of thing that these machine learning classification frameworks are partially designed for. And so coming back to SkyPortal for a second, the way it works is, once you've saved a source, for those sources that are interesting, you can trigger follow-up on a variety of resources. And so there are drop-down menus. Get to see that on SkyPortal, where you can request, a spectrum, what we call forced photometry. Forced photometry is when you have a survey and you have a particular point on the sky, which you think is very interesting, and you can take for example, all of the images going back in time and asking what is the flux that the survey saw at that particular point going back in the past, right? And so this can be very useful for example, looking at the history of a transient from another survey, right? So for example, if Pan-STARRS or Atlas found something running ZTF force photometry, maybe you can provide either better upper limits or an earlier detection or a different color, right? And so there's a lot of advantages to having multiple surveys running. And of course, things like scheduling classical observing runs, that's all taken care of here too. Okay, and so coming back to TNS for a second, so you've done all this, you've gotten your spectrum, you've made a classification, then you can report the classification of that transient to the community, to TNS, and so this is where classifications go. The other thing I just want to mention, because I don't think I had time to put in the slides, the SIMA folks have built this again, another Kafka platform that they call Hermes that allows you to post photometry, spectroscopy, interact with TNS, etc. Antoine, who is going to talk about the mobile app, but also is leading the interaction between, for example, Boom and SkyPortal and Hermes to be able to write and read Kafka streams from them. This is the place that we expect to be, for example, sending our photometry and spectroscopy going forward, because it's a really nice service to be able to share data. Okay, yeah. So a few things that something like Boom enables. So with regards to multi-messenger. So yesterday, as I mentioned, Christine and Shar talked, for example, about the neutron star mergers, these kilonovae, using that was discovered in this particular one 8 years ago now by these ground-based gravitational wave detectors. And so where this comes up is, these optical surveys do not function, in a vacuum, right? There's a variety of other wavelengths that are out there that are producing synergistic data that, again, you want to be able to cross-match with. And so the gravitational wave case is just one where the gravitational wave detectors, they are also producing alerts. Of course, those alerts look very, very different than what's coming out of the optical surveys. They tell things like time and, broadly speaking, where on the sky to look, and something about the total mass of the system, and a few other kind of data products, right? They look nothing like an optical alert. That being said, right, you can have an alert corresponding to this neutron star merger, and then cross-match it with the optical data of the corresponding kilonova, right? And so the way that we manage this within SkyPortal is we have specific pages where we're listening to what's called the Global Coordinates Network. So this is a service that's supported by NASA Goddard, and broadly speaking, many multi-wavelength and multi-messenger surveys are producing alert streams that go to GCN, and folks that are running, brokers and marshals are listening to those and then helping to do the cross match, right? And so in this, as you can see in the plot here, for a lot of these, one of the main differences to keep in mind is that often they don't tell you exactly where on the sky to look. They can, so in the gravitational wave case, you can have, error regions, hundreds to thousands of square degrees. If we're talking about other wavelengths, can be more on the orders of arc minutes or whatever, but this tends to be a cross-match problem where you need to try to identify which optical alerts are within the error regions for these other instruments. And so SkyPortal helps you take care of that, as well as can do things like tiling the sky when you want to try to cover it. Okay, and so in this particular case, if, let's say, a gravitational wave alert has come through, ZTF has tried to tile the region, and alerts start flowing. At that point, then, of course, you're scanning for candidates that correspond to just within that region. You try to down select the handful that you care about, maybe that they're fading and they're new and whatever. And then, you write a GCN and tell the community about the new transients that you found. Hopefully submitted them to TNS, submitted them to Hermes, doing all of the good things to do with the community. Okay, and so I showed a plot that was not so dissimilar to this yesterday, but this is at least one way you can kind of think about it. And this is I think some version of this was from the original SkyPortal paper. But so you have your surveys, they go into some kind of broker, so either Kowalski or Boom, they flow into SkyPortal. Similarly, if I'm I have my gravitational wave detectors, neutrino detectors, gamma ray detectors flowing into GCN, which also go to SkyPortal. The cross match can happen there. Further, you can run things like your Bayesian inference codes to try to do your classification, and this can be Bayes, this can be ML. There are folks in the audience who do both to try to do this classification step. Once you've done this classification, send it to TNS, you send it to the community, and so on. Right. So this is, broadly speaking, how a lot of this works now. And so I talked a little bit about automated discovery, but this is becoming more and more important, and it does rely on a lot of capabilities on the brokering side. And so VTSBot is the kind of the version that we've been running in production for quite a while. So Kowalski, which is ZTF's current alert broker, we use VTSBot, which has that machine learning classifier that I talked about just some number of slides ago, brighter than 18.5, deep real bogus above 0.5, etc. If it passes that, you get an automatic request to SCDM. It's Kowalski that's sending the instructions and constraints to SkyPortal, right? So it's telling SkyPortal, does it meet some set of criteria, which then can accept or reject the request. SkyPortal communicates with the SCDM scheduler to take the spectrum, as well as to save those transients to TNS at that point. SCDM takes the spectrum, ML classifier runs to classify that spectrum, comes back to SkyPortal and then on to TNS, right? So it is still quite a number of steps, but again, if, for example, you get to the point where you can take a set of alert packets that includes images and photometry, identifies the subset that you care about, and produces some ML score that you can put a cut on, all of this capability now exists. Right, so a lot of the rest of this, now we've talked a lot about SCDM, but the capability to interact with NOR Labs Aeon, for example, that is built into SkyPortal. So like a lot of telescopes that have APIs now, a lot of these capabilities just sort of work, right? And of course, it's been a fair bit of trial and error, including by folks in the audience, to make this happen, but it just kind of works nowadays. Okay, and so as I mentioned, BTSBot, cutouts, metadata, etc. And we'll get a chance tomorrow to also do this with light curves and do this in the CIDR way. Okay, so speaking of light curves, so the main difference between, for example, BTSBot and CIDR, BTSBot doesn't use light curves directly. It computes features based on light curves. And for example, age of transient, right? What is the newest detection minus the first detection and such. So it makes some of the problems slightly simpler. And so this is, for example, we have notebooks kind of demoing how to train a BTSBot-like algorithm. It just makes some of this simpler. As I said, we're going to get practice doing this with light curves tomorrow. We've done, within our group, we've done a lot of light curve work over the last year, so that we're going to get to demo that some. And so this is to some extent what makes apple cider different from something like BTS Spot, right? It includes light curves. It has the potential to include spectra. Again, these are things that Felipe and Ayer and others will demo tomorrow. Okay, so that's kind of on the brokering ML side. On the marshalling side, so we can also do this purely in SkyPortal. So this means that you don't necessarily even need access to a broker specifically to be able to make this happen. For example, within ZTF, we use this for automating follow-up for multi-messenger events that pass some criteria. Say some gravitational wave alert comes through, a plan gets made, automatically triggered, Einstein probe these days functions pretty similarly for some of our follow-up instruments. And so this typically works pretty well for these multi-messenger type events to automate the triggering. Yeah, and so this is another capability in case it's interesting. Okay, so finally, these questions of multi-survey searches, which I've made the case for. So here's an example. So this is an example taken from what we call the ZTF and DECAM experiment, which happened earlier this year. So there's a postdoc named Tomas Abumada at Caltech. He previously taught at the summer school. He helped lead a program where ZTF and dark energy camera were taking images overlapping in the sky. And so, one instrument could find the early part. So ZTF's burst detection was here, whereas the DECAM had been seeing it for a while earlier, right? And so you don't need if you just have one survey going, you will never be able to catch a transient as early as you can with multiple surveys, right? Okay, and so this is again, this is why Boom exists. A lot of the capabilities from before, Kowalski couldn't handle multiple surveys, made built-in filters hard and all this kind of stuff. And this is why we've been developing Boom, because it can naturally manage multiple surveys simultaneously. Okay, and so this has been my part. Timing wise, we're doing pretty good. And so Theophile is going to take over in the next half where we're going to actually get hands-on alert brokering stuff.
Okay, perfect. So brief reminder. So as Michael said, what Boom is this alert broker, and the architecture looks something like this. So you have ZTF and LSST that are sending you those alert packets, right? So new image minus reference image. If you find something, an alert is sent and has those images plus some metadata and light curves, only if you've detected something at that position before. And so you end up with that time series of brightness over time. And so we received this both from ZTF, LSST. Schema is somewhat similar, a little bit different. And what we do in Boom is we try to unify that schema as much as we can. And we ingest that data in a database. We run a number of machine learning models we have on the different surveys. And then we run those user-defined filters. And those user-defined filters, historically, those were done in Kowalski. That system was super similar as Boom's. And it required people to know about the underlying query language. And so you ended up with those very complex queries. That would be something like 1,500 lines, for example. That's the filter that I've been running for this demo. And now you can essentially define this with a UI that Thomas Culino at Caltech is building that looks something like this, where all that you have to worry about is what are the quantities that you're really interested in. So now what's nice with this is you remove the requirement of knowing the actual underlying query language or how the system works, and all that you're left with is just the logical operators and knowing the data product. And knowing the data product, that's not something that you can really get around of. And what we've been doing is we took one of the existing filters from an experiment called CATS 150 that ZTF is running. What that experiment does is it cross-matches every transient, or rather the broker cross-matches every transient with the catalog of known galaxies called NED LVS, so local volume sample. And then we look for every single transient that matches with a known galaxy, because that galaxy gives us its redshift, so its distance to us. And what that experiment really cares about is everything that is within a local volume, and that's defined as 150 megaparsecs from us. And so what that filter does the cross-matching, then it uses it to see if something has a potential match within that volume, and it looks if something's not a rock. So if it doesn't match with a known asteroid, because we don't care about those, it looks as whether or not this is a known star, because we don't care about those. We care about new transient, at least in the context of that filter. And if it's an artifact, so is it really a transient that ZTF has detected, or is it just an artifact of the image, some kind of data quality issue? And so you end up with all of those common operations that pretty much everyone wants to do for transient filters. Is this a star? Is this a known bogus? Is this a known asteroid? And then you want to enforce whatever experiment-specific constraint you have. And so what we did for that demo is we took that very long filter for this existing experiment, and we re-implemented it with this UI, and then we had that run through our new broker, Boom. And going back to that architecture here, maybe I can skip directly to this one. What you can see is once we've gone through all of the steps of ingesting the data, running machine learning models, and doing the filtering, we don't directly communicate with the system downstream. So it's completely decoupled, and it doesn't care about what reads from its output. So in theory, if you guys wanted to run Boom on your own laptop, you could. And you could just do whatever you want with the output. You don't need SkyPortal. It is recommended, as in it gives you a way to visualize and scan through the identified candidates. But if you wanted to programmatically do that, and once you've identified things, putting that into a pipeline and doing further filtering, that's something you could do. And so that's what we run. And what I wanted to start with is showing you guys what that would look like. So if you're a scanner, so someone who's on hold for looking for whatever is coming through those filters in real time, so you can trigger another telescope, get a spectra, classify things, you would essentially head over to that platform. And you will look for this candidate page here. And what it gives you is a choice between different groups. And those groups are where the filters are saved. And that's a big aspect of SkyPortal or any data management platform. It's not really astronomy specific. But if you want something that's generic and a lot of people can use, the assumption is within the same website, people don't have access to the same data. Just like you are in Slack, you can see some channels and groups, and I can't see them, but you're accessing the same platform. So you have some data access concept. And so different users with different interests and different data access rules have access to different groups. And it's on those groups that the filters are set up. So someone who wants to scan would say, okay, I'd like to see whatever came through a filter between a start and an end date. Usually that defaults to the last 24 hours. I care about seeing all of the candidates. But really, in a real life scenario, you don't want to see the same things over and over again as they're detected every night. So you would say something like, don't show me those that have already been saved to any of the selected groups. So if you have the filter set up on that group, candidates have passed it, you've already saved them. The next night, you don't want to see those again. So you would say, okay, don't show me things that have already been saved. And for example, for the summer school, that CATS 150 filter that we've redeveloped, we saved it on this group. So this is what you can select for scanning. And once you're done selecting those parameters, and very often is as simple as those three things, you can just hit search, create a server to find all of the transients that have passed through your filter. And when you're there, really the job of a scanner is to scan through the whole list. And so you have a number of candidates. And for example, as just so you can get a kind of an order of magnitude for this, we've processed, for the sake of the summer school, we've processed a week's worth of ZTF alerts. So I think that totaled to 1,800,000 alerts. And only 100 unique objects have gone through that filter. So you can see how quickly, even with somewhat simple pipeline, I think that's what I think this one is, you're left with just a very small number of objects as soon as you remove some of those things that you don't care about, at least in transient case. So you're left with 100 things, and you would look at those and you would see, okay, this is my new image, this is my reference image, this is my subtraction of the two. I can clearly see here there's something brighter than in my reference, as I can also see it in my subtraction. And I have some amount of data. It's somewhat limited for this object. Maybe we can kind of skip through and try to find one that looks nice, like this one, for example. So you can see it's on top of this galaxy here, and it really, really outshines it as it gets really bright. And that's why on the new image, you can barely see that galaxy underneath. You can kind of see that fuzzy thing here, but you mostly see this really bright point. And so what you're looking at this is, you're looking at this and you can say, okay, this is a supernova, kind of like transient. And you have your light curve. You see that we haven't detected it, then all of a sudden it started rising really quickly, and it got to 18 magnitude. And then it started getting dimmer. And interestingly enough for this one, it stayed somewhat red while it was getting dimmer in the G band. So that may be an interesting object for those that are interested in reddish transients. And each of those transients, they have their dedicated page. And on that page, you see a lot more than you would on this tabular format like thing. And so often what the scanners do is they look at this list, they identify things that look interesting, like this one too, and then we just click on it and see this full page here where you can comment, discuss with colleagues, you can trigger follow-up, so there's no allocations on this testing instance, but this is how in a couple of clicks people would trigger a spectrograph and just get data and classify something and send it back to a transient name server. So all of this, all the workflow and all the different steps that Michael has talked about, really now you don't need to do things with your own systems. You can really rely on a data management system like this to do that for you. And one thing that you won't see in that testing instance, so this data is from 2024. The reason why this is because we run on nights that overlap with the LSST data preview 1, and you'll see that in the upcoming notebook, where we can find transients, supernova-like transients that match with LSST, and you can get access to LSST data that's hosted in Boom and plot that alongside the ZTF data and use both for machine learning if you'd like. But most of those objects, because they're from 2024, I'm very likely to, if I head to transient name server right here, if you wait for a second, you'll see, okay, there's a match for it. There's a known supernova that's been classified and discovered. So actually, this has been discovered by the BTS Vault program that Michael talked about. And so we discovered it, and it went through the broker, automatically reported by SkyPortal to a transient name server. And thereafter, someone got a spectra for it. That's not necessarily someone from ZTF, because since it's public, it could be anyone that just wants to gather data and is interested in that object. And when things are classified, in principle, in a production-like instance, that TNS name would appear here, and you would also get the spectra and photometry from that public platform. Okay, so this is just to give you kind of a brief demo of what's the workflow. You would look at those things, find whatever is interesting in the scope of your experiment, like this one here, who's rising somewhat quickly. And whenever you found an interesting object, you would just go here and essentially just save it. And once it's saved, you have that guarantee that if I come back here, you can see there's 100 of them. If I were to scan again and I say not saved to any of the selected groups, scan again, now I'm down to 99. So I've eliminated one thing that I'm interested in. And very, very often, and I think you can see a lot of them here, there are things where it's really not obvious if it's supernova-like, if it even has a host galaxy at all, which is a constraint for my filter. So the job of a scanner is also to kind of discard things. And the mechanism for that is you can just click here and hide things, or what people often end up doing is they want to keep kind of a catalog of the things that they don't care about, so that thereafter they can select that group here and say, don't show me things that I've already saved that catalog that I don't really care about. Okay, so that's a brief demo of scanning. So you guys know this platform will stay up. And so you can do whatever you want with it. So if you want to scan through those objects, see if you can find supernova-like candidates, fetch the data, run it through some of the ML models that you've seen yesterday, that's something that you're free to do. And the API documentation, I'll share that while Antoine goes through his quick demo of the mobile application. And yeah, so talking about Antoine stuff. So Antoine has been working on developing a mobile app. The reason why, I think you guys can see it here, but really you can do this work on a phone. There's no need for a computer. And as we're getting into that regime where we're having a lot more transients and we want to find objects that are fast evolving, you want to be able to trigger something and get additional data, such as spectra, pretty much as quickly as your object starts to go through your filters. So as early on as possible, you want to identify interesting transients and do things with. And obviously, we don't really have control over the universe, so that those kind of things can happen at any time. And so we want to be able to do that on the go. And so Antoine has been working on a prototype for a mobile app. So I think he shared, Antoine, I don't know if you can hear us. Did you share the link on Slack for this?
He did, yes.
Okay, awesome. So if you guys head over to the Day 2 Summer School 2025 channel, you'll have a link. And if you're interested, you can download the link. You can download the app for both iOS and also Android. Do keep in mind, it's been developed with iOS in mind, so that's where it looks the best. But if you're like me and like almost no one in the US and you have an Android, you also have that option still. So I don't know if Antoine, are you ready? Do you want to do a quick demo of your mobile app, show people what you can do with it?
Yeah. Do you display it remotely? Yeah, here. I believe you can just input here. Are you in the meeting?
Yep.
Okay, then you'll need to screen share it on the meeting. Well, you can put Mike's computer there. That should be good. You can probably put it there if you would prefer. Yeah, just yeah.
On the screen?
The Mike's computer.
Ah.
You can put it there if you want.
Yeah, I mean, it's again.
Okay.
It's again.
All right. Can people online indicate if they can hear?
Yeah, I think we can hear you guys.
All right, cool.
And
Okay. Okay. So everyone can hear me?
yes, we can.
Okay, so we're going to do a quick demonstration of the mobile app that I am developing. So I will go here. So the features that we want to have access to with the mobile app will be quite simple. So we want to have access to the source page of candidates we want to scan, and the candidate that already been saved as a source. So here we have the page listing all the source already saved. So this is the source that Theophile saved during the demonstration. We can see here, so simple page with photometry, the image, and some information. You can have comments, spectra, and you can also request follow-up. So that can be very useful because you can only with your phone, with an interesting source, request follow-up without needing to use your computer. So you can do it very quickly. So for the scanning, you will have the same option as you have on the web page. So here we can do quick scanning. You can so select group. I mean, it's everything the same as on the SkyPortal web application. And when you scan, you will have the candidate here, the number on the top, and you can swipe to see every candidate listed. So here, this is the first one. You can swipe here to see the other one. You can see if it had already been saved. So it's not saved for now. And if you want, you can also request follow-up here and save it as a source. Okay. Maybe you can't finally. Okay, that seems that not working. Strange.
Might just be the emulation being weird.
Yeah, I don't know. Okay, so you can see every candidate here, and at the end, if you swipe for every candidate, there is many here, so I will not do it, but you'll have a quick summary of what you've done with these candidates. So I think that's all for the presentation. Someone have a question or?
I can't read.
What?
I can't install something.
On Android?
You have to do test flight
I did
first.
this flight, but SkyPortal mobile is just it starts installing, but then never does. It's just gives me an error.
It's just spinning. It might need approval from Michael or something.
Did you get the error message? Something?
What?
The error message? Did you see it?
Yeah, I mean, I'm seeing it on mine, and it's just spinning. I think it might just
Yeah.
be maybe an install number limit. Have you ever had a large number of people trying to install it all at once?
No.
So that might be it. I think you got
You
it.
got it?
Oh, I got it as well. Okay, that was great. Yeah, should be good.
Okay.
I did want to ask, I don't know if you responded in this, like, do you have a repo, like a public repo for the app itself?
Yeah, I send it.
Oh, cool. Awesome.
I update the message and send it
Awesome.
to the convo. So yeah, Theophile, I think you can take back.
Yeah, sounds good. And so you guys know, I think the idea is throughout the whole summer school, I'll be running the same filter that's looking for hosted transients, hosted nearby transients. And you'll see more and more sources pop up on SkyPortal. And so you guys can have fun and actually scan through those and save them and try to classify those objects with some of the ML models. And SkyPortal has an API. So once you have your account, maybe I can show you guys this quickly. Okay, so once you have your account, you can always head over there on the top right, that profile thing. And there, if you scroll all the way to the bottom, you can essentially create tokens to access the data programmatically. And so SkyPortal has a fully...
Okay, if you could hold off for a second.
Oh,
Are you sharing your screen, Tyler, or is it only my?
It's this. It's 1 second.
If you have a map, go to the mirroring in the upper left. And
Yeah.
you have to just remirror it. That's what I had to do yesterday.
can you guys not see the screen share?
No, it was a thing on our end for the projection. We're good now.
We're good now? Okay, cool. Yeah, so I was just saying on SkyPortal, on the top right here, you've got your profile icon. And when you click there you head over to your profile. That's the URL here, /profile. And at the very bottom, what you can get access to is you can generate tokens. And those tokens, you can then use them to query the API through regular HTTP API calls from any Python script. And so that's how we can programmatically access that data. And we might have a chance to showcase this towards the end of that second session. But the idea is that through this, you can query for those candidates just like you would from that page here, and get access to those and run machine learning models and re-upload the results, or, for example, do spectra fitting. And so that's one thing to keep in mind is that even though those systems are really built to provide you guys with the front end and a way to visualize your data, a lot of what people do with it is actually run automated pipelines to fetch data from it and kind of augment and enrich those object pages with more information. That's also something that you can do. Yeah, so I'll keep pushing ZTF transients throughout the whole week. And so based on what you guys have done in those notebooks, one thing that could be interesting to do is to fetch data for those objects and run models, try to classify them and push things back. You could also cross-match them with LSST, and though some of that will be showcased in the upcoming notebook. Okay, so I think what we'll do now, since we kind of had the break early before, I think we'll head directly to the data access notebook, where what you guys will do is directly access the broker's data. So Michael, do you know if this has been merged?
I have merged it.
Okay, cool. Okay, perfect. So what I'll do is I'll kind of walk you guys through the notebook. Instead of a regular presentation, we can just go through this. And as we go through this, let's make it interactive. If you have questions, just interrupt me or raise your hand. And towards the end of that notebook, there's a number of kind of pipelines that are written, but with missing code for you guys to go through and complete and get things done. Can you guys see my screen sharing with the notebook?
Yes, it looks okay.
Okay, cool. Remove the Zoom controls. Okay, perfect.
Yeah, there is a question. Does it work? Should this work in Colab?
Yes, you can put that in Colab.
Okay.
It does come with requirements.txt file. So if Colab doesn't have some of those dependencies, I think it should, but if it doesn't, you just want to pip install them. But this works in Colab. It doesn't require you to have any data locally because we'll be querying everything remotely from the broker. Okay. So you guys have been introduced to ZTF, what it is, what it does, what's data product, and you've been also introduced to what happens once the broker has run filters and things are pushed and things have already been identified as potentially interesting. But in between getting those alerts and having them sent to a downstream system once they've been identified, because obviously you don't want to send the 500,000 things that ZTF sees or the 10 million things that LSST will see. So you have a lot more steps in between, and that's what those user-defined filters do when it comes to doing stuff in real time. However, you have a lot of workflows, and Michael mentioned ZTF REST from Igor that I think is in the audience here. A lot of the workflows also want to look at data asynchronously, so not necessarily as it's coming in. They don't necessarily want something to run in the broker, so they might want to do something in, let's call it semi-real time, or they might want to be doing archival searches. And so let's say you're training a new ML model and you want to rerun that on past data to identify transients and objects you might have not found earlier with the pipelines you had in place. That's something that you can do. You can go back to data and you can re-query it. Though it's not really a requirement at all for the brokers. That's how they kind of all evolved, just because of the need for those archival searches. And a lot of that revolves around the same data products you would use in a user-defined filter system, right? So cross-matching with other catalogs, ML models that the broker has added, but you might also want to rerun your own. And so often what those workflows do is they would do some light filtering, not nearly as complex as the user-defined filters, but then they would do the complex stuff in Python or whatever language they're using to query that database. And I kind of like that analogy of gold panning because you have all of this shit that you're trying to look through, and there's way too much to look at it manually. And so you want to sift through it and kind of step by step try to add more and more filtering so that you can find the good stuff without losing any of it. And so you're kind of sifting through and trying to eliminate most of it except what you really care about. And so to start with answering some questions, I think we can skip the ZTF alert stream stuff because that's pretty fresh. And we can skip directly to how do we access it. So there's a number of public and private alert brokers for ZTF. But the goal of today's notebook is to kind of take a go at trying Boom, which is that new broker we've been developing. So it's still being developed. So bear with me if you do encounter an error or two, in which case you can just let me know either here or on Slack. And the goal of Boom is to not just serve as a ZTF or an LSST alert broker, but doing both and extending that also to other surveys. And not just processing those sequentially, as in, or rather in parallel, right? So separately, and just offering the same features for each of them. But what we want to do is to keep cross-matching ZTF alerts with LSST alerts and vice versa. And so that the point behind this is if you have multiple surveys, you have multiple eyes on the sky, they have different properties. So LSST can see deeper, but not as often as ZTF. And so you want to take advantage of the added value from all of those different surveys, right? So what we're really hoping to see with something like ZTF plus LSST is having really good coverage when the object is bright enough with something like ZTF and detect it often and have really full light curves. But then if you're using LSST or another instrument like the dark energy camera, you might see that object before ZTF could ever see it just because they can see so much fainter than ZTF does. And so what you have in Boom is for every single ZTF object, those get matched with the LSST alert stream. So the big difference with an archival cross-match is that it just, for an archival cross-match or catalog you're cross-matching against, it never changes. So you just need to query once for a given object, right? Because we associate objects as things that don't really move. We kind of consider them as, if you see something for the first time at a position, we create a new object, and then thereafter, when we find things at the same position, we consider it to be the same object. So that's what we mentioned by objects here. It's not always correct. It's not always the astronomical object because some things do move. You have stars with high proper motion. You have moving objects. But in the case of transients, or most things in general, they're not moving objects. That definition kind of still stands. And okay, so what you'll start with in that notebook, there's a couple of imports. And I provided you guys with some of the visualization and plotting methods just because it's not so interesting to have to re-implement it yourself, and they're somewhat survey specific. And so you have code here to plot the cutout. So there's 3 images, so science, reference, and subtractions for every ZTF alert as kind of a triplet where you can see the 3 of them together. And you also have a method which, given a light curve, you can plot. You can actually plot that and look at what that looks like. And the third thing that I provided to you guys is an Python API class that kind of abstracts all of the actual HTTP API calls to request data from the broker. So that way you don't really need to care about how does the broker work per se when it comes to just communicating with it. And you can just focus on how to write queries and find things and actually identify interesting transits. So I'll skip through these. You can just assume that they work. They should. And the credentials that are here, those are public and they will exist for the time being. We'll probably keep them going because this is anyway pointing to testing instance. So you can go back to the notebook even after the summer school and re-query ZTF data. Okay, so as Michael mentioned, Boom is running on a non-relational database called MongoDB. And so in that paradigm, you don't have a well-enforced schema. So you want to enforce your schema upstream of the database, so before you actually push data, and sometimes also when you query it. And they just look like JSON documents, right? They just look like Python dictionaries. So for example, if you were to look at your alert collection, it might just look like this, where you have the ID, that's the unique identifier. It's always the same name, _ID in Mongo. And so here, if you're looking at, let's say, your alert table, that would be your unique candidate, so your unique alert identifier. And you would also have an object ID. So as I mentioned, that's purely positional. So if you detect something, the first time you get a new object ID, thereafter things detected at the same position get the same object ID. And so this is what you kind of use to name your transients and look for them and query data. And because they're documents, they can be nested. So as you can see here, there's this field called candidate in that document, which itself is a document with a number of fields, like the position of the transient, the magnitude error, and when it's been detected in Julian date. So this is, as you can imagine, a super trimmed down version of what this actually looks like. There's really hundreds of fields in those, but actually those quantities are often the one you care about the most. And similarly to how the data is actually stored in the database, the filters are also JSON. So unlike a relational database where you have to always specify what you want to select from what and what are your conditions, here you can, that projection, so what you actually select and return, it's a lot more flexible, but it's also optional. So you can just return the whole thing at once. And what you really care about most of the time is first how you want to filter through things. And the filters, they look like this. So let's say I wanted to find candidates where the magnitude is dimmer than 20, for example, so greater than. I would do something like this. I would say my candidates, my PSF, and you can notice this dot notation here. This is how you access nested fields. So when you have a document within a document, and that can be repeated forever, you would just have the top level dot and the key that you want to access. And this can be repeated for as deeply nested as your document is. And then you would say, okay, what's the operator that you want to enforce on that field? So in that case here, I want to look for things with a magnitude PSF that is above a certain value. So I will have this greater than operator. So I have a ton of arithmetic operators. And I think you can kind of get a sense that it's not a hard query language, but it is very verbose, a lot more than Python, in my opinion, especially as you start building more complex pipelines. You have all this indentation and you have to repeat things very often. So things get pretty big. Hence the user-defined filtering building UI that I showed earlier, where this is kind of all abstracted. You just need to focus on the data and what you want to do with it. But yeah, so this is super simple example. You filter in one field, and by default, your different conditions, they're enforced as end conditions. So all of them need to be satisfied. However, because in Mongo, you can have an operator for everything, you have an OR operator, so you can say, okay, actually, I want one of those conditions to be satisfied for it to be true, for my statement, my condition to be true. And so let's say you wanted either your DRB, so that's one of the ML scores, or the real bogus, that's kind of the model that predates the DRB. You want one of those two to be above a certain threshold. You can just have your R conditions, and then the condition themselves, they look pretty much the same as this. And then when you have something like this, it's specified as a list. Okay, so that gives you kind of a brief idea of what a non-relational database query looks like. Most of the, by the way, this is transferable it's not just MongoDB specific. This is transferable to whatever non-relational query language you want to use. Most of them look very similar to MongoDB, especially for those basic arithmetic and logical operators. Okay, so now we know what the database looks like, how we can query it. We have a vague idea of what the data product is. And so something that's valuable is to kind of just jump in and run a somewhat complex query, and we can kind of go through the conditions that we want to enforce. And the idea behind the query that is set up here is to do something very similar to this CATS filter that was run and that pushed data to SkyPortal. The only difference is I'm not using that cross-match with a known galaxy catalog. And instead, I'm letting a machine learning model called SI, which is a phenomenological model, which tries to guess, okay, is this hosted in a galaxy? Is this nucleus at the very, very center of a galaxy? Is this a variable star? Is this an orphan transient, so not hosted in a galaxy, but also not a known star? Or is this bogus? And we run all of those models in the broker when we do that like data enrichment part of the pipeline. And so at filtering time, when you do your archival searches, all of that is available. So you can use all of those ML models we've already kind of pre-run for people. And so what this filter does is very similar to the CATS filter. We look for things that are real, so with a high DRB value. We look for things that haven't been detected too many times, because often, at least in that context, those could be like variable stars or known objects, right? Like if you've detected them many times, you're likely that they've already passed some kind of filter before. And at least in this context, we're interested in things that are new. And we're looking at if this isDiff field is set to true. So what this field is, it's simply a Boolean that checks if in your new image, the thing that's fluctuating in brightness is brighter or dimmer than in the reference. So for a genuine transient, like a supernova, this should always be true, as in you have nothing in that position and it goes boom, and now you can see it and it's bright. But in the case of something like a variable star, that might be very different because that star, it's permanent, it's in the reference. And so when you detect it, it could be that now it is fainter, right? It's varying in brightness. It could be fainter than it is in the reference, in which case this is false. So enforcing that to true is also a way to get rid of some alerts and kind of focus on things that are brighter than usual. And we make sure that things aren't near a known solar system object. So that's a field that's given to us. There's the distance to the nearest solar system object. That's this SSDist NR field here. When it's missing, the pipeline upstream sets that to a very high negative value. So you can just say, okay, if it's negative, then there's no match to a known solar system object. So that's a quick way to get rid of those. There's some data quality flags here, stuff like how many bad pixels or how many previous alerts were flagged as bad at that position. And is the image quality good enough? And as I said, okay, is this a known star or not? We also have ML scores for those. And interestingly enough, this ML score does not come from ZTF at all. It doesn't look at the ZTF data. And that just goes to show that when you have multiple catalogs and things might be detected in multiple catalogs, right? So just as we were saying, you could see something in ZTF and LSST, but also for stars, you'll likely have seen those, 10, 20, 50 years ago. And so if you have an old catalog and you've already kind of classified things, you can just reuse those results. And so here we have this SG that stands for star galaxy score. And if it's high, it's likely to be a star. And it gives you the distance because, again, it's not running in the ZTF data. It's not necessarily the ZTF object. So what you have is just two fields. You have the distance to the nearest object in that other catalog, and the score, this star galaxy score that run on the object from the other catalog. So instead of just saying, okay, I want this to be low, as in it's not a galaxy, I can say, okay, it can be low, or the object I match with can be far enough from mine that anyway, it's not an actual match. So I don't care about that value, and I don't want to restrict things based on that. And what I did here, so as I said, instead of relying on an actual match with the catalog for seeing if things are hosted, here we relied on this SI hosted model. And so we have that constraint saying we also want a high score for this that tells us that this is really likely to be hosted in some kind of galaxy. So the big difference with the other one is there's no cut on distance, and you're not relying on whether or not a person has added that galaxy to the catalog before. If you can see that galaxy in the image and the model can pick it up, it will be able to provide you a score that you can filter on. Okay, so that's for the query itself. And throughout the whole notebook, we're just reuse the same query absolutely everywhere. That said, this is very kind of supernova-like. So if you don't care about those, you're free to change that query and just look for other things. If you want to look for variable stars, if you want to look for things that are nuclear, like TDEs or AGNs, you can just edit this filter to, say, not look for things that have been detected multiple times. You might say, okay, well, I don't care if this is hosted, so you might remove that cut. And actually, SI, as I said, it comes in different flavors. So you also have this SIN for SI nuclear model. So you could in theory remove the hosted and look for things that are nuclear instead. So it's as simple as this. Okay, so let me keep that query for now, and we'll just run through it. So let me rerun from the first cell. Okay, let's give it a second. Maybe I can switch to my other environment and find that. Okay, perfect. Okay, so I run through the first cells with the already predefined methods, and I'll go to the query. Okay, so you would run this, and this is running on the entire ZTF alert set. One thing to keep in mind, you would absolutely never do this in a real life scenario. If the survey's been running for like 7 years, like ZTF, you just have way too much data to just run on the whole thing at once in one query. It's not just bad for the system you're querying, but your computer will die. It will return just too much data, and that would not fit in memory. So
stop any astronomers, as you know, Theophile.
no, it does not. That's part of the problem. And so, I mean, one way to actually help with this is you might not care about returning the whole document at once. And so in Mongo, you have this concept of a projection. And so you can say, actually, from the data model, I know that I have this and that is available. I don't want to return the whole thing. And so you could say, okay, I just want to return the object ID, the candidate ID, and the candidate object. I don't care about the classifications. You could remove that. And then in whatever you receive, that will not contain the things that you've not decided to include. And similarly, you can actually reverse that logic. A projection either includes or excludes. So if you wanted to say, actually give me everything but one field, you kind of just do something like this, where you would define the field name that you're not interested in, and you would just set it to 0. So that would just exclude it from the projection. And so for the sake of that example, let's just return most of it. And you can see here, we found 2,456 alerts. So when you think that the whole thing that we have in a database, we have almost 2 million of them. And with a query, with a couple of lines like this, we're already down to 2,500. It kind of gives you an idea that even though the surveys, they detect a ton of things, when you formulate your queries correctly and you have a good number of constraints, you can really, really sift through most of it and very quickly be left with a very small sample to actually analyze and look at. And so the question is, sure, we found 2,500 alerts, but what's the total number of objects in the database? So I said around 2 million before, and you can actually run that query with Boom. You can just say, okay, please count whatever is on that catalog. And also, why not just get the length of whatever you queried, compare that to that total and get a percentage. And so here you can see with that simple query, we're down to just 0.1% of alerts in that catalog. So it's pretty simple to really trim down everything. And the only difference in the production-like system, where that survey has been running for years, is that here you would basically add a constraint where you would say, okay, I just want to get candidates that have been detected between some start and end dates. And similarly to how when we were scanning, we're looking at the past 24 hours. If you have a pipeline that's running in semi-real time, that's also what you would do. You would just look for things within one JD of the last date or something like that, to just look for new things so that you don't rerun on things you've already analyzed earlier. Okay, so we're down to 0.1%. We don't have that much left. And now the question is, out of those 2,500 alerts, how many of them are actually unique objects, right? So we likely observe the same thing multiple times. And if you were to just look for the unique object IDs, because that's what tells you really what are the unique number of objects that you have in there, you would be left with just 1,000 of them. And in that cell here, what we also do is then we create the ZTF alert aux table. So aux just stands for auxiliary. The idea is that compared to the alert table, where again, if you have detected something multiple times, you have multiple alerts for it, and so you have multiple entries. This table here indexes things on the object ID. So really what it is, it's an object collection. So you have one entry per unique object ID. And those entries, they contain those different properties. They contain the previous candidates. So that's an array of previous detections. That's effectively your light curve. They contain cross matches. So it's a dictionary with the catalog names as keys and the list of matches from that catalog as value. So this is the data enrichment that we do, where we cross-match with a number of catalogs. And so for the summer school, I've only set it up with this net catalog. And so if there's a known host galaxy that matches with any of the transients in the database, you'll have that information available. And then the added value of Boom specifically is that we have this aliases dictionary, where you have the survey names as keys and a list of object IDs from that survey that match with your object here as values. And so if you look at the entry for a ZTF object, you have these aliases and you have a key called LSST. And if that's not an empty array, that basically means that yes, your ZTF object has some kind of LSST counterpart. So actually in a couple of cells, we'll look at this and see some concrete examples of objects that have LSST matches and look at their data. And yeah, for context, the way we did this, because LSST is not really running and sending us alerts in real time yet, they released this data preview 1 data set, and we just went through it and we kind of created fake alerts and ran them through the broker. And so what you end up with is, just like for ZTF, you have this object collection here, we have an LSST object collection. And so then we process the ZTF data from 2024. So those are dates that overlap with the time when the images for the LSST data preview 1 were taken. And so what you're left with is ZTF alerts that potentially match with LSST. Okay, so quick look at the previous candidates. So here we create the actual objects, and that contains all of those fields, including the light curve. And so what we can do is we can just pick a random object from our list and just plot it and see what it looks like. And that's exactly what we do here. We call the plot light curve method that I gave you at the top of the notebook. And we get the random object's previous candidates and its ID, and we get it plotted here. So I got kind of lucky, got a random one from this 2,500, and it's definitely a real looking object. And what we'll do later in the notebook is do the same thing, but try to include the LSST data when we have it. As far as the cross matches go, so as I said, here we're only cross matching with Ned. But if you were to look at any of those objects from those 2,500, or rather 1,000 objects that have match with Ned, so that's a subset of that has a match. And that actually gives you a sense of scale, right? With that ML model, we said, okay, give me things that are hosted, so things that look like they have some kind of galaxy underneath. And that gave us 1,000 unique objects. And if we only looked at those that match with the catalog, it's actually like around 400. So you might ask yourself, the 600 left, what is it? Is it that there's no actual host and the ML just messed up? Or is it that the host isn't cataloged? So that's something that you can see if you were to look at the images. Okay. And then last but not least, as I said, we have those matches with other surveys, and that's really the added value of Boom. And so if I were to pick a random LSST object within that sample, I can see that, okay, this LSST object match with, this ZTF object match with this LSST object, which unfortunately they don't have a nice name like ZTF does. But I think that that's probably due to the actual sheer volume of things we're expected to get. And funny enough, we have only one. There's only one object within all of those objects that we found that has an LSST match. Okay, so we might want to see what that data looks like and see how we gather it. So this is the light curve of the object itself. And now what we can do is, okay, we know it's LSST object ID that corresponds to it. So we can do the same thing as before. We can create the alert aux table, but for LSST and say, okay, give me data with the ID of the matching LSST transient, return the light curve. We get that light curve. We see there's 19 detections in it. And then we just plot it. And okay, so we get that plot. If we look at the axis in JD here, it's somewhat time coincident with this, between 25 and 50 plus this. But you can see that it matches. And so the LSST detections are somewhat in the middle of that ZTF light curve. Now the question is, what would it look like together? And one thing you can kind of notice here is the magnitude scale is different. ZTF, we see it around 19 at peak. Here in LSST, we see it 21.5. We literally never see it fainter than 20.2 in ZTF. So there's probably something wrong. And surely enough, if you just concatenate those two and you plot them, okay, that doesn't really match. That doesn't look all that great. That's a quirk of the LSST data preview 1 dataset. And that's due to this image difference algorithm where we remove from a science image, a new image, a reference image, and we're left with this abstraction. And what happened here is the reference image from LSST, they're pretty much as old as the science images. And so what happened is the new transient, whereas in the ZTF reference image that are some years old, there's nothing at that position. The transient was not there yet. For SST, the transient was already there in the reference image. The reference image are just too close in time from the new images. And so what happens is that then what you're getting is a magnitude. The flux that is used to compute that is just the difference from the reference. So if you have nothing in the reference, the flux that you have is essentially the flux of your transient. But if you already have something underneath that bright object you just detected, then it's that the flux of that bright object minus the flux of what's already in your reference. And so that's the problem here, is that you end up with less flux in LSST than you do in ZTF because the transient's already in your reference. And so that explains that shift here. So quick hack for this. And if you guys end up looking for other transients or even specifically everything that match with LSST, I believe there's probably around 300 in this ZTF alert collection that we've set up for the summer school. You'll have the same problem pretty much everywhere. But you can make a couple of assumptions. If your assumption is this is a new transient, hence there's nothing in the reference, there shouldn't be too much of a difference if you compare the science flux from LSST, so that's the flux measured directly from the science image. So you don't do any image difference, you just get the flux that you see in your new image. And what we have in ZTF, right? If there was nothing before, the subtraction should not make much of a difference. And for LSST, we've also provided not the magnitude PSF, which is the image difference data product, but we also have this magnitude science and sigma magnitude science here. And if you plot that instead, okay, it does look a little bit different. And also the magnitude scale, that's way closer to ZTS where we peak at 19. And surely enough, if you kind of trick your method here and you kind of create this new LSST-like curve where you basically replace the magnitude PSF by the magnitude science, and you plot your LSST object along with your ZTF object, now we end up with something like this. It's not perfect, but it's a lot more reasonable. The LSST data nicely overlaps with the ZTF one, minus those detections here that might be still offset somehow. Not entirely sure why, but overall, it matches nicely with the SST transient, with the ZTF transient. Okay, so now we had a concrete example of, I found an object that's supernova-like, that's hosted in some galaxy. It's definitely not a rock, it's definitely not a variable star. It matched with SST, and I can make use of that data, not just to plot it, but if you wanted, you could use that as part of a pipeline, right? When you concatenate those two light curves, here we're just displaying it, but you might as well, for example, fit the light curve and see how quickly it's rising or fading, and we'll actually look at this on ZTF data only in a couple of minutes. Okay, so now we looked at light curves, we looked at cross matches, we made use of multi-survey information, which to my knowledge, I think Boom is the only broker where you can do this so far. And what we haven't looked at are the images. So quickly, we just pick the transient here, and we'll query the images collection. Similarly, we have an alert collection, we have an object collection, and we also have a cutout collection. And that's indexed on the candidate ID. So it's a one-to-one match with the alert collection. So the alert collection itself does not have the images because they're large, and 99% of the time when you're trying to just identify transients, you do not care about the images. You often want to retrieve those towards the end or for ML applications. And so we decided to separate that into another collection. And so you can just get the candidate IDs from your previous candidate array, and you can just query for all of the alerts that match with this. And so for this object, it looks like we had 6 alerts in the database within this 1 week that we ingested data for. And we can look at the first one, and it looks something like this. Unfortunately, this one is a little noisy, but you can see in your new image, there's a galaxy and there's something a little brighter on top. You can see what you have in your reference and what you're left with your subtraction. So as noisy as it is, this clearly looks like a real transient. Okay, so as far as the data exploration that is really, really guided goes, this is pretty much it. And what you guys have to do as an exercise is something which is inspired by Igor's ZTF Rust. So if he's here, sorry, Igor, but people might want to bother you with questions. But what you have here is a method which is the pipeline that's defined, and all of the data querying and retrieval is somewhat provided. But what's missing is all of the logic to actually identify fast evolving transients. And so this, as I said, somewhat similar to ZTF Rust. So what do we want to do? We want to run some query to find transients of interest, then query light curves for all the unique objects we found. And for each band, so for each filter, right, you have your light curve and you have images that were taken with different filters. So effectively, you have one light curve in different colors and different bands. For each band, we want to go over the light curve, find the magnitude that is at peak, and split my light curve into all of the data before I reach my peak, so as my object was getting brighter, and the data after I reach my peak, so when my object is getting dimmer. And for each of those parts, check if we can satisfy some constraints on the speed of evolution of that object. If the object is rising more than 0.3 magnitudes a day, or fading at quicker than 0.5 magnitude a day, then I want to select it. So the goal of that pipeline is to look for really rare transients that are evolving somewhat rapidly. So the cuts here of 0.3, 0.5, they're actually not that constraining. The reason is those fast transients, they're somewhat rare. So if you're running on a week of data, you're likely to just not find anything. So you can kind of tune this to make it as low or as high as you want. But those were good values to end up with at least 10-ish objects that you can look at. And that would be exercise number 1. So that would be following the instructions here. What are the different constraints? So that's your minimum viable product. What do you need to implement for this? And so it's really guided. There's notes about common problems you'll have to face, because if you just take your data and you just do a super simple linear fit, that's not really enough. You need to ask yourself, okay, I have magnitudes, but they have some error associated. if I have my brightest and my dimmest point, is the difference between those two significant enough? And also, you know, you need to have a sufficient number of points for a linear fit to be actually meaningful. So you have a couple of things to go through. So you can basically just pick wherever there's a 3 dots and a to-do, and you have to implement stuff to get this to work. And the idea is once you have identified a number of fast transients, to go over here and do the second exercise, which is coming up with your own custom plotting suite where you just combine the images plotting and live curve plotting to have a composite plot where you can have a given transient and show a proper kind of info card or information about your transient with everything you think is relevant to figure out what this is. Okay, so that's it for this notebook. So what I'll do now is I'll ask you guys, do you immediately have some questions? Did you run into some problems running this? And otherwise, we'll just do this asynchronously. So I'll stay here on Zoom muted. And whenever you guys have questions, you can ask me.